Perfect. Okay. So let's resume at this slide. I think this was the last slide that we delved into yesterday. This slide is like a summary of the main calculations that you can perform using equation of state. So we need some inputs. The typical inputs are the composition of the fluid in terms of components and the amount of each components in the mixture, and we need some experiments to be reproduced by the equation of state. So each one of those components is characterized by some properties. So the critical properties are relevant. The eccentric factor is another one. And as we are dealing with mixtures, we need to input a new parameter that is the interaction coefficient parameter that we discussed yesterday. So using those inputs into the equation of state, we are able to predict density, fugacity, and to use the equation of state coupled with another equation to perform equilibrium phase calculation. It means to calculate how much of our mixture is in gaseous phase, how much of our mixture is in oleic phase. Okay, this is the main applications for the equation of state. Yesterday, let's recap some key topics that we explored yesterday. Yesterday, we used we defined the PVT simulator as a black box, where inside this black box we have an equation of state. We can have correlations to predict the viscosity, for example. Okay, and the main output of this PVT simulator are the inputs for the numerical simulator simulation models. So if you are working with a black oil if you are working with a black oil simulator, the output is a PVT table, a black oil PVT table. If you are dealing with a compositional model, you need to input an equation of state in that model. And if you are dealing with a thermal model, you need a table, a k-values table to input to represent your fluid. So those are the main outputs that we need to do. Our main goal is to export these outputs. All those outputs needs to be exported by the simulator. You export this, and our goal is to use this output in the numerical model. Just to recap, a numerical flow model has basically 7 sections of information. The first section is the input-output control. Okay. The second section is the grid and the petrophysical properties of the grid. The third section is the fluid section. So this section will receive the information exported from the PVT simulator. So our goal here is to export this output, and this output will be the input for this section. So the PVT simulator generates the input to be set in this section of the numerical model. Numerical model is the model that you use in IMAX, in GEM, or in STARS, for example. So in this case, this numerical model has extension of dot. Okay, this is the extension that you need to use in that models, using the commercial package from CMG. Okay, the fourth section is the rock fluid section. Here's the section where we can set the real perm and the capillary pressure curves in our model. The fifth section is the initialization section, the initial conditions. In that section, we need to set the solution of the problem in the time zero, how we can start the simulation, how to kick off our simulation, what is the pressure at the time at the time zero, what is the initial pressure, what is the initial composition, what is the initial bubble point for a black oil simulation, for example, everything I need to set the initial conditions. The sixth section is the numerical control. And the seventh section is the wells and recurrent data. This last section is the section where we can set the wells and the groups in our model. Okay, so the PVT simulator will be key to set the fluid model, but the initial conditions also can need some piece of data from the PVT simulator. For example, if you want to set a compositional gradient of your fluid, a variation in the properties or the initial composition of your fluid as a function of depth, you need to input this information in the initial condition. And this information comes from your PVT simulator as well. So the basic difference among those models are the way how you model the fluid model and the initial conditions. This is the basic difference among those kind of models. So we start doing this yesterday. We start using some experiments in our PVT simulator. In that case, I didn't export any output from the numerical simulator, the PVT simulator, I mean. In that case, I just conduct a simple exercise where we input a couple of lab experiment, and we just saw how the EOS can predict some properties, and we compare those properties, these predictions against the predictions, against the measured data from the lab. So basically we did this yesterday, and we used in that exercise three or four source of data. So the typical experimental data that you need to input, the first data is the composition. We need to know which components are in your mixture and which amount. Okay, you need to, it's the makeup of the mixture, okay? The mixture makeup. You need to input this in your model. The second piece of information that we inputted yesterday, it was the saturation pressure. Remember, it was a gas mixture, so we need to input the initial pressure and the saturation pressure just to set two ranges of pressure. We have our first range of pressure that comes from the initial pressure. Everything is conducted. Oh, sorry. Everything was conducted at constant temperature. So the temperature is constant. Okay, you have a specific temperature to do your exercise, and your experiment starts at the initial pressure, and you in the lab you can simulate a depletion experiment. So the pressure will decrease. You pass through the saturation pressure, okay, and you have the final pressure is the room pressure, atmosphere pressure. So this first range is the undersaturated range, and this other range is the saturated range. Okay. During the undersaturated range, there is no change in composition. The composition is constant. It's only expansion because you are decreasing the pressure and the volume of the oil is increased in volume. Okay, the volume of the oil is expanding because you are reducing the pressure. So, but during this period between initial pressure and the saturation pressure, the composition is constant because all the gas is in solution in the oil. There is no gas releasing from the oils. All the gas, all the light component that will be released as a gas phase at low pressure, at this level of pressure, everything is in the liquid phase. So in this case, this part of the experiment is called constant compositional expansion, okay? And this other part from the saturation pressure through the atmosphere pressure is called differential liberation. In this case, there will be gas. So gas will be released at each pressure level. If you reduce it from the saturation pressure to the next step, gas will be released and you will remove the gas from the chamber and you will run the experiment without the gas. So more gas will be generated in the next reduction in pressure. So this is the idea. You can remove the gas released every pressure step during your experiment. So we have a specific keyword to set the data from this experiment in WinProp, and we have another keyword to set this data from the differential liberation WinProp as well. So those are the third one, the third part, it was CCE. The fourth, it was the differential liberation. And the last one, it was the separator. So yesterday, we simulated a case where you have your fluid, your oil, everything is oil because the pressure, it was the saturation pressure. So at the saturation pressure, if you reduce the pressure to separation pressure at temperature of room temperature, okay, you generate oil and gas. Part of your mixture will be gas and the other will be remain in the oil phase. So in this case, we can calculate the GOR of this experiment. So you can calculate how much of your gas was generated from the oil. So you can report the GOR for this case. This is the GOR during this step one of separation. However, the oil phase goes into the tank, and the tank are at the atmosphere pressure and room temperature, okay? And more gas is released during this phase. So if you have more gas, you have an additional GOR released during this stage. So this is the volume of oil 1, G1, 1. I will call this 2. So the volume of the gas during this stage, this final stage, divided by the oil volume, allows you to calculate the GOR in the second phase. So the total GOR during this experiment is the sum. Just add the GOR measured during the phase 1 plus the GOR measured during the phase 2. This is the total GOR. This is a very simple However, very useful experiment and allows you to dimension the separation conditions from float units, from for stations units at onshore environments. So this lab experiment carried out with a small amount of the fluid gives you information about how the final volume of the oil, how is the final volume of the gas during or after some stage of separation, okay? Some surface separation stages, okay? You can measure another additional piece of data that you can get from this kind of experiment. You can take this oil, the oil 2. The oil 2 is called the dead oil, is the oil without gas. All the gas is considered already released from the oil. So it's only oil at room conditions, at room temperature and room pressure. So if you measure the density of this oil, you can convert the density to API degree. So you can report the API. So remember, the API is always a measurement of the dead oil. The API does not represent the oil in the reservoir. The API represents the oil at the surface conditions, at room temperature. Okay, it's the density of the oil at room temperature, at room pressure. So this is another information that you can get. And the final information, you can compare the volume. You can compare the volume of your oil at saturation pressure at the saturation pressure is the conditions where your oil has the largest volume. It's the point in pressure where you have the maximum volume of the oil. Okay, if you divide the maximum volume of the oil at this condition, at the saturation pressure, I will call O, over the volume at the tank conditions, I will call O2, you have the maximal uh, uh, shrinking coefficient of the oil. It has the maximal shrinkage reduction in volume of the oil. Okay, for example, in our example, this is around 2. Okay, the oil, the reduction in volume will be reduced by 2 times of the maximum amount at the saturation pressure when all the gas is released from the oil volume. It's a very typical for very light oil volume. Okay, so this is just a summary about the data that we input yesterday, and we noticed that the equation of state was not able to reproduce all those data. So there is a deviation when you compare the raw results from the lab versus the results that you get from the prediction from the equation of state. So you need to do something. Need to perform some steps in order to tune some parameters in the equation of state in order to get the match. So our goal from now is to do the fit between the prediction of the equation of state and the behavior that we measured in the lab. Okay, let's discuss how to do this. Before, let's just give you some ideas about viscosity modeling in GEM, in IMPROP, and consequently in GEM. So before going to the calibration, okay? Before go beyond, someone has any questions? I can go, or someone has any additional questions to raise?
It's fine, Marquinhos.
Thank you. Thank you, Aline. Okay, so let's explore the viscosity modeling. We have 2 options in GEM. We have the JST, it's the famous JST correlation model, and we have the Peterson model. Peterson is one of the reference that I shared with you yesterday. Okay, is the main author of that book, Dr. Christian Peterson. Both correlations are available in prop and consequently in GEM, because you need to export the parameters of those correlations to use the same correlations in GEM. Okay, so everything's coupled. The prediction for gas is very good. Okay, sometimes you don't need to fit for gas. However, for liquid, it's mandatory to perform some tuning steps to fit the liquid density that you measured in the lab. For liquids, you have to do. Okay, you have to fit the data. Okay, the prediction with default coefficients is poor. It's poor. You have to do some steps. Okay. JST is more flexible than Peterson because JST has more coefficients to be tuned, so have more flexibility to do. So sometimes JST can handle multiple samples at the same time using the same group of parameters. But Peterson may be more accurate for oil, especially for heavy oil. So if you are working with heavy oil for gas miscible flooding or for steam flooding, probably your model will be better captured using Peterson correlation. So heavy oil, it was the main motivation for Dr. Peters to develop her famous correlation. Okay, so this is just to give you an idea about the equations. Okay, this is the GST correlation. Basically, a polynomial equation. It's a very simple polynomial equation. You have some mixing rules in the polynomial, and you have some coefficients. So sometimes you can use you can tune these coefficients in order to get to fit the lab data. So this will be our approach. We'll try to optimize those coefficients to match the lab data. Okay. Peterson has less degrees of freedom, so you have less coefficients available to be tuned when you compare with JST. So have basically three, six, five. We have five coefficients to be used. Those coefficients are applied to this mixing rule. The mixing rules to compute the molecular weight of the mixture. So you can tune those coefficients in order to predict the viscosity of the mixture. Okay. And let's go get to the chase. Let's go to the regression strategy. Is our goal today is to explore some clues. I will share some clues about how we can conduct this regression, because our problem is an optimization problem. We have an objective function, and this objective function is the difference between the prediction of the equation of state minus the lab data. Basically, this is the problem. We need to reduce this objective function. We need to minimize this objective function. Basically, of course, the way how we code the objective function is not simple like that, something more elaborated, but here just to give you an idea how about the problem that we are trying to solve. So we are trying to minimize this objective function. So to minimize objective function is an optimization problem. So basically, to do a regression on inside the PVT simulator is to do optimization of a specific objective function built combining predictions from viscosity model or from equation of state in relation to the lab data. Okay, basically, this is the problem that we will try to handle. Okay, and we can try to set some recipes to help us to follow to solve this problem. So I will share some ideas from myself, from the books, from the course that I have taken during my career. Working with compositional model, working on compositional fluid characterization. So this is a big summary about some ideas, some strategy that you can use to to succeed in this task. Okay, so first point. Okay, I can go. Any questions? Are you prepared?
Yes.
Okay, let's go. So let's go. First point, use as a few regression parameter as needed. So don't pick all the possibilities that you have. Be very pick and use some criteria to select which variables, which parameter uh, you will tune in your equation, in your exercise. Okay, I will discuss how we can select the key parameter that can help us to reduce and to optimize this objective function. Okay, but let's start as simple as possible. Okay, this is the idea. In summary, start simple. Just few regression parameters to start to know. Sometimes few parameters is needed to succeed in this task. You don't need to combine excessive number of parameters. Okay, this is the key message of this statement. Okay, another point. Try to choose regression variables that combine high impact and high uncertainty. This is key for us, okay? So some parameters are more uncertain than other. So you should you should pick this parameter to be tuned during this process. So this process needs to combine high level of uncertainty and high impactful properties. So be challenged to do this. Some examples. The binary interaction parameters, are very impactful parameter because they can control the attractive force among the components. Correlations parameters are the parameters from the viscosity models, are very impactful parameters as well, and are uncertain. There is uncertainty, intrinsic uncertainty related to them because, as I said before, the correlations are very accurate for mixtures, especially lean gas, dry gas mixtures. However, for liquid, you have to do some tuning. So those correlations are very useful to be tuned to get the calibration. Okay, and the other one is the HVS component, pseudo component. So yesterday I showed you that there was a component called C7 plus. C7 plus is the heaviest pseudo component in my mixture. Everyone that has more than 7 carbons are included in this pseudo component. So it carries the highest uncertainty among other components in my mixture because we don't have a pure component. It doesn't represent a single component, a pure component. It doesn't represent a isomer. It represents a lump of component, and those components are very different. You can have here components with 7 carbons, but you can have components with 20 carbons. and you are characterizing this component using a single set of properties. You are using a single value of only one value of critical pressure, critical temperature, and a centrifugal factor. So you are modeling things different, like you are consider that bananas, apples, pears are the same thing. In other words, just to clarify. So this is the idea. So this parameter, the heaviest component in the mixture has the highest uncertainty among the other parameters of my mixture. Okay. Um, the variables range is important. So you can after picking the key parameters, you should take care about the range that you will consider to vary in order to tune those parameters. You cannot, you need to preserve some consistency among those parameters. You cannot assume that the heaviest component has a lower critical pressure when compared with methane. There is some quality control that you need to ensure just to preserve the thermodynamic consistency of your model. Oh, this is key for us. Okay, this is very important for us. Do not regress properties of pure components. Pure components, you know about that. You know which are the properties which are the properties to characterize the pure components. You know what is the critical pressure, the critical temperature of pure components, and you know the amount of each pure component. So there is no uncertainty involved in those components. So don't regress on those properties. So preserve those properties, in other words, okay? Another key clue for us: don't match at the same time simultaneously viscosity and PVT data. Do it in separated steps. Take a look here. I'm assuming that first you will match the equation of state. Just after matching the equation of state, we'll go ahead and match the viscosity correlation, step by step. Okay, first step equation, second step viscosity. Don't do at the same time. Don't do at the same step. In other words, don't include viscosity data and PVT data inside the same objective function. Build one objective function for equation of state and regress on that. After doing this step, after conclude this step, go build another objective function only with viscosity data and regress on that. That's basically this. Okay, it's not a science rocket. Okay, it's just just go step by step. This is the key message from this point. Okay, and in summary, this kind of exercise is a try and error exercise. You need to do several steps. You need to try again. You need to test different weightings. Okay, you can put weights in your variables, so you can say that saturation pressure is more important than BO in my objective function. So saturation pressure, we will receive a greater weight than BO. So you can play with weights in order to do this regression. Okay, is another way to do this. Okay, so this is my key points for you guys. So please take a look at this later and save this slide, because this slide has several experiments, several tests behind it. So I built this slide considering my experience and other experience from other authors. So they are very key to do this kind of work, okay? So this is the methodology that we will follow. We will use WinProp as the package to do our simulation, PVT simulation. So WinProp will be our PVT simulator. Okay, you can do the same thing using PVTP or PVTP or PVTsim. Okay, and the regression parameters will be for equation of state. As I said before, we use the plus component property because this plus component is he brings the highest level of uncertainty among the properties of my mixture. The coefficients, the binary interaction coefficients will be used, and the volume shift. I didn't mention the volume shift in this slide, but you should include volume shift here, okay? Especially to predict the density of liquid, especially for API. So volume shift should be included in this list because we know that the equation of state has limitations to predict liquid density. So you need to work with a third parameter equation of state to do it. And if you don't tune the volume shift, the default value is 0. 0 is like to work with a two-parameter equation of state. So to include a third parameter, you need to have a value for volume shift different of 0. So not to do that, you need to include this as an uncertain parameter in your list. Okay, so plus component, the component of the pseudo component is included, volume shift, and the bips. Basically, in summary, those are the more uncertainty parameters in our mixture. For viscosity, the coefficients of the JST model can be used for viscosity matching, and the mixing rules in the Peterson equation also can be used for the matching. Okay, depends on if you are working with JST or if you are working with Peterson. Okay, depends on the how most of the models use JST because JST is more flexible, so it has more degrees of freedom, so it's easier to match multiple PVT viscosity data with JST. Peterson has good application, but as I said, especially for heavy oil. So we'll do this. We first will, here is two step. The third step is solubility, but it's not included yet. So here is two steps for a while because we are dealing with only with PVT data and viscosity data. The first step is to perform the equation of state matching. After that, we will update the parameter, the new parameters of the equation of state. Using these updated parameters, you can go to the second step. And the second step is to do the viscosity model match, keeping frozen, this is important, keeping frozen the parameters obtained in the previous step, okay? You don't match equation of state and viscosity at the same time, at the same step. Do equation first, update the parameter, keep it frozen these updated parameters, and go beyond to match the viscosity model. Two steps, okay? Two separated steps. Sequential, but in separated steps. This is just an example to show you a case, a more complete, more complex mixture of oil. You have more components involved in this mixture. You have from CO2 to C20 plus. So in this case, this sample is newer than the other sample that I used during the exercise with you guys. So now you have more accuracy in the lab experiments, especially in the gas chromatography. So now we can distinguish uh, uh, among more components. So you can separate the heaviest components from the light components in your mixture. So you can more precisely know which are the components involved in your mixture. Okay, so this is done using a technique called gas chromatography. So with the evolution of this technique, you have more capability in separating the heaviest component in your mixture. Nowadays, you can find some fluid analysis with C40 plus. C40 plus. If you work with a lab that works only with fluid, they have the best equipment to do this, and they can distinguish in C40 plus, C50 plus, depending on the mixture of oil, the composition of the oil that you have. In Petrobras, we standardize to work till C20 plus. C20 plus, most of our samples has the description from CO2 to C20 plus, okay? Everything with more than 20 carbons are included inside this pseudo component. So all the critical properties, the eccentric factor of those components are represented by a single set of components. So this explains why this guy is the less accurate input data in my mixture. So it needed to be tuned. So we'll tune this in order to reproduce the lab data. So this is our goal for today, to do some tuning in order to get this result. These in dots are the experimental data for RS, solubility ration, and for BO, okay? And the dashed curve is the prediction using Peng-Hobson, and the other is the prediction using SRK, okay? So both are very comparable, so you don't have a huge difference between them. Here there is a slight deviation in the prediction of the saturation pressure. This is the saturation pressure. One is less accurate than other to predict the saturation pressure, but in general, the prediction is pretty good. It's very comparable, okay? So this is our goal for today. Input the data that we input yesterday, but now we need to do some tuning steps, okay? Let's do some tuning steps before exporting the final data to be used in a numerical simulation. Which kind of data is relevant for us? For oil, if you are working in an undersaturated oil reservoir where depletion or water flooding are the recovery methods applied to produce this oil, you need to have bottle samples to preserve the in situ composition of this oil. If you don't have bottle samples, you can recombine the gas, flash the gas at surface conditions with the dead oil in order to mimic the composition of the in situ fluid. But it's not the ideal, okay? It's not ideal. The ideal, the best for fluid modeling is to have bottle samples, downhole samples, okay? And you need to sample amount of the fluid and to carry out several experiments in the lab. So the separator, as I mentioned, is very relevant. The CCE is very relevant because it's part of our strategy to operate over the saturation pressure. In other words, to operate in the undersaturated range. So this, the way how the fluid behaves during this range is very relevant for us. We should be very accurate in representing the fluid behavior measured by this experiment. This experiment is key for us, okay? This experiment can be key, however, it assumes that the pressure is below the saturation pressure. This is important because only in this experiment you have gas released. So to calibrate the gas properties in the reservoir conditions, you should have a differential liberation available for your fluid. And viscosity, as I said yesterday, viscosity is another experiment. So you need to carry out in a separate equipment to measure the behavior of the viscosity above and below the bubble point, okay? And those are the data generated by those experiments. BO, GOR, densities, viscosity, oil shrink rate, okay? The reduction in volume of the oil, the gas properties, okay? And the bubble point, the saturation pressure, okay? Those are the points. For gas, which are the main mechanisms to produce gas reservoir? Gas reservoir, basically, you produce by blowdown. So depletion is the natural mechanism that we explore to produce and to recover gas from the rock. So it's important for us to know about how the gas behaves with pressure change in porous media. So the volume variation of the gas is controlled by the Z factor. The Z is the same thing of Bg. Bg is the pressure at standard condition over the temperature at standard condition times the temperature of the reservoir, the Z over the P, okay? If you know Z, you know Bg. It's the same thing, okay? Viscosity is important for us, and the composition. Composition is mandatory. For condensate gas, you have more properties because condensate gas can generate condensate in the reservoir or at the surface condition, or both. So you need to know more about how the phase behavior of this gas. So the phase behavior in this case is more complicated because it's not a single phase behavior. You can have a two-phase region even inside of the reservoir when you are operating a retrograde condensate gas reservoir. So in this case, you need to measure in the lab the cumulative amount of condensate produced. It's called forgot the name. Oh, I forgot the name, but I will remember the name of the property of this property. Liquid dropout. Okay.
The experiment is CVD.
CVD, yeah. The experiment is CVD. Thank you. Okay. So these are the data that we measure in the lab, and it's important because with a small amount of the fluid of the reservoir, regardless gas or oil, you can predict how the recovery mechanism will behave. So it's very interesting to see if your recovery method based on depletion can be efficient or not. Only depends on the fluid behavior. The fluid behavior will control part of the performance of your recovery method, the reservoir. So another important point to discuss, and I would like to share with you guys, this slide from Dr. Kurt's Whitson course, is the accuracy in measured data. As I said, our goal is to minimize objective function. Okay, you need to minimize objective function. So the question is, what is the minimal error that I can admit in this minimization process, in this optimization process? This objective function should be less than which error? This is the idea. How accurate we should pursue during this optimization process. Let's do this choice guided by the accuracy in the lab data. I don't need to reduce my objective function less than the accuracy of the lab data. The lab experiment sets the minimal error that I should admit during this optimization process. For example, saturation pressure. What is the typical accuracy in the equipment, in the procedures, in the lab? Typically is more or less 5 bars. More or less 5 bars is the same thing in terms of lab data. If you have a saturation pressure of 100 bars, it means the same thing to have a saturation pressure of 105 bars, because the accuracy of your equipment, the accuracy of your procedure gives you this limitation. This is the minimal uncertainty that you have related to this property. So you can use this criteria to guide us to define what is the minimal error that you need to pursue during this optimization process. So this is another key slide for us. I ask you to preserve this slide because it can be used for multiple applications. So you can use the same criteria to compare if your because this question is very common. How I know what is a good when I achieve a good optimization during my PVT simulation? What is this point when I can stop? In other words, when I can stop to do the optimization? You can use this table to guide you. Oh, okay, here I have I got a good reduction, so my data basically has the saturation pressure is around more or less 5 bars in relation to the measured saturation pressure. So basically, I can consider this data fitted. So now this part of the work is done. I can move to the second part. Or let's see another property. For another property, for example, gas. Gas has accuracy in Z factors around 1 to 3%. Tá? Another thing, tank oil density, API. In other words, API, 1%. Okay, well, API is very accurate, very easy to know, it's very accurate to measure API. So you need to calibrate API in a very accurate way. Density at reservoir conditions, because here is more complicated, because in this case you have gas in solution. Here's that oil only is a single phase, okay, it's simple. But in this case you have gas, so it's very pressure dependent problem. So you don't have only one value, you have a curve as a function of pressure, and obviously function of pressure and temperature. So you can admit greater errors. So you can admit an error till 4%, okay? Except last stage, because who I accept last stage? Because the last stage is the saturation pressure, and the saturation pressure is the dead oil. Is the dead oil is the used to calculate API. So the last stage, you have more, the data is more precise. So you can reduce your tolerance, okay? You can increase your tolerance. The GOR in the differential liberation expansion, 3%, okay? The release of the gas. BO, 1 and 2. BO is very easy to fit, okay? 1 and 2 you can achieve easily with a few steps. GOR, this is the GOR and the separator GOR, okay? Is the separator GOR, 2%. Gas CVD and gas recovery, 2 or 3% of tolerance. Oil BO in condensate BO. This oil in this case is condensate, okay? It's the oil generated during the depletion of gas reservoir. It's the condensate. 5%. It's very hard sometimes to match this data. Condensate gas is challenging. Condensate gas is very challenging, okay? Oh, now another property very key for us, the minimum miscibility pressure is important where you are inject gas, CO2 or hydrocarbon gas over a specific pressure in order to ensure the miscibility. So if you want to simulate a miscible process, you need to operate over the minimum miscibility pressure. And you can measure the minimum miscibility pressure in the lab. You can measure using rising bubble apparatus or using a sling tube test. You have some ways to do this. Dr. Ali Danesh in his book discuss about it. You can check, I think, chapter 10 in his book. I have this book in the reference list. You have a discussion about the minimum miscibility pressure measured from sling tube test or from rising bubble apparatus. There are two ways to measure this. And the minimum visibility pressure from those experiments has tolerance over around 5 bars, okay? Viscosity. Oh, viscosity is challenge in the lab. I don't know the reasons why it's challenge, but especially challenge in heavy oil. So in heavy oil is very common to accept 20% in deviation between the prediction of the correlation and the measured value from the lab. So it's very common to admit bigger errors when you are dealing with heavy oil. Okay. Gas viscosity for lean gas, usually you don't measure in the lab. You use correlations because the correlations are accurate. So you measure only for condensate gas or mixture, such as mixture between hydrogen and other gas in order to mimic the cushion gas role in porous media. So you discussed on Friday about mixture between hydrogen and other gas. In this case, you have to measure the gas viscosity. And it's very challenging to reconcile multiple samples of gas viscosity using the same correlation. In this case, JST, I think, is the more flexible correlation to model this kind of viscosity. Okay. So let's go back to this exercise and let's apply some ideas that I share with you. So we discussed about strategy to fit our data and strategy to compare how we can stop or when we can stop this tuning procedure. Okay, let's go back to this, and after that we can try to start a gas case. This case is for oil, and I have another one. It's the gas phase. We can start doing the same. Let me know if you have any question, please. Feel free to interrupt me anytime. So I will open my CMG launcher. In just a minute. Okay. Okay. As I said yesterday, I'm using the latest version, but you can do everything in a previous version, 2024 or 2023, no problem, okay? All the options that I'm exploring the course are available in the previous versions of WinProp. There's no there is a bug in one version, 2025, but I will comment on Friday. Let me open the exercise that we did yesterday. Okay, we stopped here. We compared the prediction of the equation of state. Remember, the curve is the prediction, is the calculation obtained from the equation of state, and the dots are the lab experiment. The green curves are related to oil properties, and the red curves, I think it's red, yeah, red's related to the gas properties, okay? We, we noticed deviation in the CCE results. So there is a deviation, and this experiment is key for us. Remember, I just discussed about ranges of operation. You have two intervals of pressure above and below the bubble pressure. So if you are intending to produce this reservoir under water injection, probably your goal is to operate over the bubble pressure. So if it's part of your strategy to produce and to operate this reservoir over the bubble pressure, you should be, actually, you must be very accurate in representing the properties of the CCE, because the CCE is the representation of your fluid above the bubble pressure. Remember, the bubble pressure is 4,000 psi, and all the pressures in this table are related to the pressures over this the bubble pressure. So this property is the most important in terms of controlling the controlling the volume variation of the fluid. Okay, how we can fix this deviation? So let's go. Let's do. I will save with another name. Let's save with case 2, step 2. Okay. I just save with another name, not in order to preserve the previous case. There is no undo or redo buttons in WinProp. Okay, so it's very important to save every step, because you are not able to recover the previous step. Okay, you needed to do everything from scratch. So it's very useful to save with a different name, just to make sure that you have all the step preserved in your machine. Okay, and during this step, let's start our regression. So the regression button is here in the interface. There is a button here. Oh, there is a disable. Let me hide this panel. Okay, hide it. Oh no. Okay. Can you see my presentation? Can you still see my presentation?
Yes.
Yeah, okay, perfect. So there is a button here, regression parameters, okay? I will click on it, okay? And here I can pick the parameters that I want to tune in order to match my equation of state, okay? In order to calibrate my equation of state relation to the lab experiment. But before that, I need to include the experiments that I want to regress, okay? In this case, the regression parameter is at the same level of the experiment. I need to pick the experiment and to put inside the regression parameters, because only in this way WinProp can consider this as part of the regression strategy that you are planning to deploy, okay? So you can click with the right button of your mouse. You can cut the experiment, and you can click again now over the regression parameters keyword, and you can paste into reg block. So now the saturation pressure is part of the regression strategy that you are working on, okay? You can do the same thing with the other keywords. You can do one by one if you want, or there is a smarter way to do this. There is a model operation here, model operation. You can click on it. You can select the keywords that you want to operate. So I will select the 3 experiments that I didn't include yet in the regression. I will select to cut them. Okay, yes. And now I will insert them using the right button in the mouse and paste here. Okay. Yeah, perfect. Let me change. So let me change the order because I like to start with regression. I like to have the regression parameter as the first one. So now all the experiments are in the regression block. Okay, everything is inside the regression block. You have pressure, saturation pressure, you have the CCE, you have the differential liberation, and the separator. Okay, the separator here. So let's start the regression. The first part of regression, we need to pick which parameter I want to tune. Which parameter I want to tune. And any recommendation, an idea?
C7 plus.
C7 plus, okay? So C7 plus is our direct choice to start the problem. So let's pick the critical component. We can start with 2 critical properties, PC and TC. A centric factor as well. You can do. You can pick volume shift because you need to calibrate the API. So let's pick those parameters. Just click on it. In the second tab, we can select a correlation. Is that correlation that I mentioned yesterday the same correlation? Okay, the same correlation that I discussed with you guys is the correlation that is implemented in WinProp. Is this correlation here? So WinProp allows you to calibrate, to tune the parameters of this correlation. This correlation will be used to compute the binary interaction parameters. So this correlation has 2 parameters, A and B, and you can regress on that. Okay, so you can just click here. When we click here, you are selecting that correlation to be regressed. Okay. Viscosity. Viscosity, the third tab, the third option. However, remember, let's start doing the EOS regression. After that, we will do the viscosity regression. Okay. For now, let's skip this part. Don't include viscosity and equation of state parameters in the same regression loop. Okay. And now let's see our experiment. Saturation pressure, okay, weight 1. I want to fit this data. This data is very important for us because the regime, the pressure regime, will control it by the saturation pressure, as we discussed before. This parameter is very important because all the variation in volume, in oil volume, will be controlled by the BO. The relative volume is another way to control the relative volume of the oil as expressed by the oil formation volume factor. The differential liberation has information below the bubble point. So you have the BO, you have the GOR, the solution GOR, the density, the oil density, and the gas properties, because in this case, now you have gas. Gas is released during this step. However, take a look here. You have viscosity. You have viscosity in this table. But viscosity is not included yet in our regression strategy. So how to remove viscosity from our objective function? Just put a weight 0 on that, okay? So let's assign a weight. The first row is the weight that you can control the weight of this property in the objective function. So you can, to remove a property from the objective function, you can erase, you can delete the 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 the, the, the entries that you typed before. Is one way to do is delete the values. You can delete, but it's not practical. It's more convenient to input 0 here and automatically you remove this property from your objective function. Clear? So for now, just remove for a while.
Marcos,
Yeah, sure.
I have a question about the real experiment. The Z factor, in this one, the gas Z factor, is a two-phase Z factor or the single-phase Z factor?
Single
Is it
phase.
single phase?
In this case,
Right
single
now-
phase.
Right now, in I think you might have observed it in the recent experiments, they provide the two separate Z factors, like two-phase Z factor and single-phase Z factor. And most of the commercial packages, they don't have the option
Mm-hmm.
include the two-phase Z factor. They only have option of like just Z factor.
Yeah. You are right. Yeah, you're right. I think WinProp doesn't have how to set the two-phase Z factor. Another way to handle is to work with cumulative oil production. So if you work with CVD or another experiment for gas, CVD, or even I think it should be CVD. You have, for CVD, you have the liquid saturation. Oh, you have the two-phase here. You have the two-phase. So now you have. In the past, they used to have only the first columns. So now they added the two-phase. Okay. So the two-phase consider the variation due to the gas and the oil in the Z.
Thank you.
Okay. Good question. And the last keyword is the separator. The separator has 3 entries: the BO, the GOR, and the API. You can include all of them in your objective function, no problem. And let's run our first case. Okay, let's run this first case. Let's save and let's run just to see if we can match the data. Let's go back to the plots. You have more plots now. I like to see the summary plot. Okay, the summary plots comparing in this case the BO before the regression in green and after the regression in red. It's better. It's better than before, but it's not ideal yet. Okay, it's not ideal. But someone could ask me, oh, Marcos, but how is the error? How is the level of error related to this deviation? Another way to see these results is to look at the simulation output. If you take a look at the simulation output, there is a second tab here, Out File. If you go down, there is a table somewhere here. This table is key for us, okay? Please save the name of this, write down the name of this table, summary of regression results. This table brings the deviation in error, okay? So the saturation pressure, the deviation here is the absolute deviation. So if you are considered to see in percentage, it's 3%. This is 3%, 2.9%, okay? 2.9%. Or in terms of absolute deviation, is the saturation pressure is the experimental data is 4,047.4, and the prediction after regression is 4,000 343. So it's more than 100 psi of deviation. 100 psi is almost 8 bars, right? 8 bars. 8 bars is greater than our tolerance. So 8 bars, our tolerance is 5 bars. I can tolerate a deviation of error of 5 bars, but I cannot consider a deviation of 8 bars as accurate. So we need to do something. We need to improve the prediction of the saturation pressure using this equation of state. Okay, so it's not good yet for saturation pressure. Let's take a look at the other properties. ROV is the relative oil volume, is 10 minus 3. 10 minus 3 is less than 1%. Let's see our table. Let's see our table. BO's here, between 1 and 2. Okay, between 1 and 2. Okay. Also, in other words, less than 1% is more than accurate. So we can consider that we got good results for BO above the bubble point. Okay, this is important because if you look at the graph here, it seems that the deviation is too high. Okay, but take a look. It's important to see the values in the scale. Another way to do this is to double check the table, because the table has the computation of the error. So when you see the same results, but in terms of error, you can consider that the error is good. The graph give us a wrong idea about the error, but here we can see that the deviation can be tolerated, is in agreement of the lab data. However, below the bubble point, we are facing a big deviation. So now we have 7%, 90%, 2%. So in other words, this should be improved. Okay, we should improve the solution for the below the bubble point. The same for GOR, the GOR. Okay, each value is related to one pressure. So we have several values because you have several pressures. It's pressure steps. Okay. DL is the density of liquid. ZV is the Z of the vapor phase. Okay. SGV is the single gas. Oh, I forgot. Oh, the gravity vapor. Yeah, thank you. Is the gravity as the gravity of the vapor phase. Mu is the viscosity of liquid. Okay. Mu L is the viscosity of liquid. And the separator data from this keyword is here. Here we just have 3 pieces of data. We have GOR, BO, and API. Okay. And they are not accurate. So the GOR is too high, 31%. The BO is still high, 6%. And the API is too high. The deviation is too high, 11%. So we need to do something more. We need to work more to improve the prediction of the equation of state. It's better, but we should improve more. So I like to start with the saturation pressure. I recommend you to try to improve the saturation pressure. So you can, for example, input a greater weight. Let's try 3, for example. And let's run again just to see if we can improve the quality of the prediction. Let's go back to the table. It's not good yet. The deviation is still high. Let's improve. Let's put 5. Let's go back. Oh, now it's better. Now we have a deviation of, now is, I think now is can be, now is calibrated. Now it's pretty good. Now is, yeah. If you convert this to bars, I think is within our tolerance. Okay. I think now, oh, sure.
So is there any limit of how much weight can we put on any of the variables? Like, so you put initially 3 weight and then 5. So is there any limit that we can put on, like, or any range or maximum limit that we can go for the weight?
Good question. Good question. In terms of the software doesn't. Software allows you to put any weight that you want. Okay, if you want to put 500, you can put. There's no limitation from the on the software end. Okay. Some authors recommend some consistency in defining this weight. In the book of Dr. Danesh, there is a discussion about how to input weights to do this kind of experiments, okay, numerical experiment. But for the software, there is no limitation. There are some technical limitations on that. There is a table. I can share the table. I can include the table from Dr. Danesh in the presentation for you. Okay.
Thank you.
I think he recommended for saturation pressure the maximum weight of 20. I'm not sure. Need to double check. Okay. I have the book here close to me. I think the book's, yeah, the book's over there. I can double check later. Okay. Weighting factors from Dr. Ali Danesh. Okay, the bubble point, he recommends maximum of 40 as a weight factor. Okay, density 20, properties related to volume. Volume is related to BO, includes RS, GOR. Okay, you can use maximum 10. Composition is not part, we don't change the composition, but other pieces of software, they have the options to change the composition, especially for gas condensated reservoir. So it's one option, but he recommends not to use composition, not to use weight for composition, only for pressure and density and volume properties. And he didn't include viscosity, but viscosity is done in another step, so we don't need to combine PVT and viscosity data in the same objective function. Okay, one table for you. This comes from this book. For the next course, I have to include this new slide. Okay. Thank you for asking, Sadan. Thanks for giving me the opportunity to bring this table for you. Okay, so back to our summary table. Now I think we are good for this saturation pressure. We are good for BO. Okay, especially over the saturation pressure. For the other properties, we are almost good. We are almost good. 1%, 5%. We are in the limit of the tolerance for some properties. These properties, the separator properties, we need to improve. We need to work on that. Maybe we can include some weights, additional weights on that. We can put more weight here just to see if we can improve the prediction of the separator properties. Let's see there. Is it still high? Okay, is it still high? I included the we can try to include more volume shift, other properties for volume shift. just to see if we are able to match especially the density. No, it didn't work. Let's remove back. Oh, I forgot to include the molecular weight. Okay, now it's much better. Okay. Oh, but now the saturation pressure, I need to double check. I think now I increase the error. Maybe you should include, try another weight. Now we start the trial and error. Okay, we need to perform some steps, trial and error, in order to reduce one. Here now I'm back. I fit the experimental data. I'm accurate for BO. I'm accurate for API, but I'm not accurate for GOR yet. Let me double check if I didn't make any mistake here. Let me double check if the
I think there are two separators.
yeah, I forgot to insert the
One.
second one. Thank you. Yeah, there is another one. Let me take from this example. Yeah, there are two. I included only one. Okay, let me include the other one. Paste after. Let me see. Let me see the weights that I used. I tested before.
I have two stages, but still the GOR and API are out. Yeah, same. What weight did you use for the separators? Two. Yeah, two. Okay.
Each line here is one separated separator. Okay, we have two separator, one separator for each line. So I think
also, Dr. Marcus,
oh, sure, go ahead.
in the second stage you mentioned like separator is 50 psi. It should be like 64.7, right?
Yes.
The pressure levels. In the pressure levels, like if you check this should be 64.7.
Oh yeah. That's true.
Because both of them are.
Yeah, I need to include the saturation. The good. Thank you. I need to include here the 6.7, right? 6.7. 6.0.
Because the environment.
Yeah, I forgot to include the atmospheric pressure.
Yeah.
Yeah. This saturation pressure is calibrated. BO is calibrated. The error is very low, very low. Okay. Oh, now it's better. The GOR is not calibrated, but the other properties are calibrated. We can see.
You are in API or
Yeah, I'm gonna check just to show how the BO now is perfectly calibrated. This property is key for us for the undersaturated range. Below the bubble point now is calibrated as well. This is the BO, the gas property, okay, the gas density. Oh, the viscosity. I need to calibrate the viscosity. Okay, we are working only in the equation of state, but the next step is to calibrate the viscosity. It explains why the viscosity the error is too high, because I still need to calibrate the viscosity.
But Marcus,
Sure.
the oil density is out, but we have a good match on gas density. Like if you go to the plot on DL, like
This,
yes,
the gas density.
the oil density is higher.
Oh, the oil is green. Yes, but let's see in terms of relative error. The oil density is here, so the error is around 3 or 4. Is according to our tolerance. Okay, sometimes the graphs can give us a wrong idea, but when you compare the error, you can see that it falls within our tolerance. So for oil density, 2 and 4 is okay. Okay, we are around this value, 3, 4, 6 sometimes, but the pressure here is very low. I'm not expecting to operate at very low pressure, so we need to take some practical choice for this kind of exercise. Okay.
Dr. Marcus,
Sure.
what numbers did you change for the separator?
For the separator, I just changed the pressure in the second separator. I included the atmosphere pressure.
Okay.
Okay.
Okay, thank you.
Because I had forgotten to include the atmosphere pressure. Okay.
What about
Thanks.
Can you show us the weights again, please?
Say it again, please.
I was saying, can you show us the weights again for the separator?
The weights. In this case, I'm not using weights. Okay, just one, but we can try. I will give you these examples to explore more. The idea is not to finish the exercise, just to give you a motivation to start and to explore more and try to get better results than mine. Okay, so for now, I will consider that this exercise is done. Okay, this part is done. We got good results for saturation pressure and for the constant composition expansion. Okay, so it's good. We need to improve the separator, especially the GOR. There is a challenge point here to improve this. We can play with the weights. We can play with the weights to do this. But for now, I will consider that we are done with this part, and I will move toward the viscosity matching. Okay. For the next step, we need to do something very important step. Okay. After finishing this point, we need to update the component properties, because during the regression steps, we got new values. Look, those are the variables that we pick to match. So PC, TC, eccentric factor, molecular weight, volume shift, and the correlation to calculate the binary coefficients. So those values had initial values, but now we got final values. I need to say to improp, please delete the initial values and assume the final values. Okay, I need those final values were obtained after doing our regression. But I need from now assume those final values as the values in our component properties. To do this, you should go File, Update Component Properties. So now the equation of state is updated with the new properties to characterize the plus component and characterize the interaction coefficients of your mixture. Okay, and now we are done to follow to the viscosity matching. So before that, please save. I recommend you to save with another name just to preserve the previous step. Let's save with 3. Okay. Now we need to remove everything related to PVT. For example, equation of state is already done. I just finished the calibration of equation of state. I don't need more to use those parameters in my objective function. So I can remove them. I can remove the interaction coefficient, and I can add the viscosity parameter. The default viscosity parameter is the JSAT, viscosity correlation. Okay. If you want to move to Petersen, you need to go to component selection here, and in the third tab, you can pick the Petersen model. Okay, but let's start with JST. Let's start with JST. Is the default option in Uniprop. Let's keep it in our model. Let's go back to regression parameters, and let's pick the polynomial coefficients to regress. Okay. You can add more parameters. There is a VCVisc. It's not the critical volume of the equation of state. Is a critical volume for the viscosity model. If you want, if you need, you can add more freedom in your regression. It's up to you. Okay, let's start simple. Let's start only with the polynomial coefficients, and let's build our objective function. Now our goal is to match only viscosity. So we need to remove everything related to the EOS from our objective function. One way to do this is to put weight equals 0. So let's put weight 0 for saturation pressure. Let's put weight 0 for relative volume. And let's put weight 0 for everything but viscosity. Everything has weight 0 but viscosity. Okay. Let's do the same for separator, because separator is not related to viscosity. There is no viscosity measurement in the separator. Okay, so we can put 0 here, and we are done. So we are done. We can save, run again. We can see the results in the graph. Here's the viscosity. So it seems fine. It seems that it's calibrated. Now, before, the behavior was like that, was represented by the green curve. Huge variation. The prediction is more than, I don't know, 7 times the lab experiment. Now we got good results. The viscosity model was able to fit the lab data, okay, after performing this regression. We can double check the errors. You can go back to the table if you want. In the table, there is the mu L. Mu L is the viscosity of liquid. And remember, the tolerance for viscosity is till 10%, some case 20% if you are working with heavy oil. So in this case, the prediction is around 5%. So 5% is very good for viscosity, for oil viscosity. Okay, so we can consider that we got our fluid. We got our fluid model. Now the fluid is updated for equation of state, and it's updated for viscosity. You can go to file again, update it. Yes. And we can save with another name. You can disable the regression because we are done with the regression. And we can export, for example, we can export the gem file. Sorry. Oh, let me hide this. Just a minute. Let me hide the panel. Okay. There is a button here for EOS, Gen EOS. I can input the temperature, 176. I can run, save and run. If I go to File, View Gem EOS, you got your fluid model. So you got the fluid model. The fluid model, after all the calibration steps, are here. Okay, it includes the equation of state. In this case, we are working with Peng-Robson. Include 9 components from CO2 to 7 plus. Include all the parameters, all the properties of for these components: PC, VC, TC, eccentric factor, molecular weight. This is the matrix for the binary interaction factor. This is the volume shift. Take a look. We have a non-zero volume shift value is related to the C7 plus that we needed to match the experiment, the API. And here is the coefficients related to the viscosity model. Okay, the viscosity model is here. Is embedded in the equation of state. Okay, it's embedded. And those are other parameters, omega A, omega P, paracore, and the enthalpy for thermal. This is only useful for thermal calculations. If you need to turn on the thermal model of GEM to take advantage of this matrix. Okay, so this is the final output. This is this output.
Marcus?
I'm about to open for question just to show you this output. So we created this output for GEM. So this EOS calibrated is this file. Okay, this file means this output to be used in a GEM data file. Okay, okay, so we finished the first exercise. So Saddam, feel free for a question.
Yeah, I have a question about the gas viscosity in the you did not include that in the regression. You only included oil viscosity for the regression. What's the recommended approach in terms of because we have the Mayer gas viscosities, but in terms of regression, we only included oil viscosities.
Yeah, because in this case, the gas is the gas in solution of the oil. So this gas is dry gas. So for viscosity of this gas can be well predicted using correlation. So you don't need to measure the viscosity in the lab for the gas. However, for gas reservoir, because in this case it's an oil reservoir, for gas reservoir, you should have a measurement for the gas viscosity. The next example, we will explore a gas reservoir. So in this case, you have gas viscosity measurement. Take a look here. Where is the gas viscosity? No, we don't have. I don't have. Sorry, I don't have viscosity for gas in this case. But in the real life, we should have gas viscosity available to be matched for gas reservoir. So the practical answer is you can have gas. In this case, you can have gas measurement, but you don't need, because the prediction with the correlation calibrated for oil gives you very comparable results. Okay, so in terms of practice, you can generate the gas viscosity using the calibration done for the oil viscosity.
Okay.
It's clear?
Yeah. What if we have a volatile oil and we usually below the bubble point, the liberated gas is a rich gas, right? So in terms of volatile oil, the liberated gas is rich gas, and where you have some variations in viscosity, which is probably not consistent with the dry gas correlations. So in that case, what would be the impact if we do not include the gas viscosity and during the regression part? Like in this case, like we have DL, we have gas viscosity below for the DL experiment.
Okay.
But we did not include in the simulation.
In this case, I didn't include because I forgot, but you could include. You could do the same step. Okay, the way you can include here, and you can do at the same step with the oil viscosity. They do both simultaneously because the correlation is able to predict oil and gas viscosity. It's clear. I forgot to include, but they have. I think they have this. Yes, they have a column for gas viscosity here. You can include and you can run together oil and gas viscosity. Okay. I forgot using. I never input gas viscosity in the case of oil reservoir because I know that this gas viscosity is not measured, it's calculated. So between the result, the outcome from my calculation and other calculation, I prefer to work with my calculation because I have control about the model that I calibrated to predict oil and consequently to predict the gas. So it's a technical choice in this case. Okay. But for gas reservoir, I would say that's mandatory to include the gas viscosity because gas is the key fluid in your reservoir, okay? Especially gas condensate. Okay. So the next step for tomorrow, for Friday. Let's keep tomorrow because for Friday, we will discuss the gas property for recovery. We discuss the lumping of components in order to reduce the amount of components in our mixture. And I will show you how to do this using this practice, this exercise. And we will discuss the gas properties for storage. So yesterday and today is for oil. So, and Friday we'll dedicate the day for gas mixture. So gas, you can use the same procedure to recovery project or storage project. It's very similar. The only thing that is different because in storage project we have to include the solubility calibration, and solubility is not common in recovery to be considered in recovery projects. Okay, so it's the only difference between them, but we will discuss on Friday.